Good morning, everybody. So I'm here from France, and I'm working for an oil company, which is Total, the fourth international oil company in the world. But I'm not here for speaking of Total on oil and gas, but for the initiative, or European initiative, for Exascale. So our objective there is to build a vision and a roadmap for what we have to do to have efficient exascale applications. So the first speaker speaks about what are the following of the next machines and next computer. But in this case, our real objective is to how is it possible to provide efficient applications. We know that the machine could be built. We hope that we effectively reach the objective of the power and so and so and so. But if we're continuing our work just as today, the efficiency of application in the Exascale computer will be less than 1%. That means you will spend a lot of money for buying your computer, for buying your electricity, for everything, for only 1%. So the question is what we are to do to be more efficient. So these initiatives take place first in US in 2008 and managed by Jack Dongar. And evidently, we are in Europe in late. So we have begun two years later, and we try to find something new just now. So you surely know a lot of things about what are the scale of the Exascale machine, but the first thing is certainly we have to provide right forecast for rare events in terms of climates, in terms of Earth. So that means we need a lot of computing for that, and we are not at the right place for that. The scalability of the climate codes are not very correct. We have to use better and better our algorithm for using that. And effectively, we know that for providing floodings, providing tsunami, we need a lot more for computational by using more and more accurate modeling. Second place, we spoke yesterday, people speak about the HPCAC program. That means astrophysics, and the square kilometer area needs a lot of data, and we try to find something what just the beginning of the Earth, just after the Big Bang theory. So the other place also are meaning by the engineering industry, and that certainly the originality of our European initiative. That means in this European initiative, we are mixing academic and industrial partners, and most of the industrial partners are coming from the engineering. That means we are coming from electricity, nuclear plants, coming from seismics, coming from Total, for example, and coming from a lot of things due to the combustion, coming from aeronautics too, with the large Airbus and the EADS company, coming from also for people coming from the combustion, like Safran, and coming from the new materials, and coming also for a human brain project in Europe, and for the drugs industry. That means a lot of people are coming from pharmaceutical industry. And all these guys of industries put together with experts what are the needs for the Exascale applications. So that's I have a lot of slides in my presentation. You should have on the report. I skip a lot of them. This one, for example, explains only what we are. So just a little works. We assume that the Exascale is exasflop for computing, but also we need exabytes. That means that at the same time, we should have some Exascale for computing, and at the same time, we should have data, big data problems. Generally, the new simulation provides a lot of petabytes of data. What is necessary to do for the storage of this data? Is it necessary to have in situ processing of this data, certainly, because we have to compress a lot. Because as Jackie and a lot of people mentioned before, that the main problem in the future should be the data communications. The problem is we spend a lot of power in data communications. So we have to provide, we have to avoid, we have to reduce this communication by algorithm, but a lot of things by compression, but in situ, not after it. So that's the reason why I want to speak that a lot of people are talking about the machine, but only one point. The capacity of the machine with the factor 1,000, and the memory is only factor 100. That means we will divide by 10 the memory space by core. So that's the reason why we have to rewrite all our codes. That's the reason why. Because today we have too much space for memory in our code. In the future, we have to divide by 10 the amount by code. So everything should be rewrite. I'm sorry about that for all people are coming. I'm an industrial. I know what it is the price. And the price for rewrite our code was much, much, much larger than the price of the computer. But if we want to have an efficient application in the Exascale, we have to change our code. We have to change a lot of things. Jackie mentioned that. I think that for taking advantage of the Exascale, we need some 1, 2, or 3 breakthroughs in all parts of our development. So just a figure for ESSI. ESSI is a real European initiative, and our goal is to climb with us maximum lot of experts coming from Europe, US and everywhere in the world, for giving us what is necessary to do, to change. So this initiative was divided in several working groups. The first one is dedicated to what should be done in training for people. The second is related to it is necessary to have a co-design center, as Jackie mentioned, or a center of excellence. Is it a vertical center? That means by domain, science domain, or should be an horizontal co-design center? That means by methodology. So that's the question, and we have to solve and give some orientation for that. Second, which is the most important, this is the industrial application. What industrial application needs for Exascale. Second, this is the enabling technologies, and the enabling technologies is mainly dedicated to algorithm, numerical analysis. And the other one is the cross-cutting issue. This is the new things, I think. The cross-cutting issues is what is the general purpose we need for all types, all science applications. So in resilience, for example, how is it possible to recover your data when there's a break? And we know that for Exascale, it will be impossible to have the reproducibility of your code, of your results. So that's proved now, even at the petaflop level. So what is the reality, what is the real results of your code? So we have to work on this point, of course. And one thing is important, this is we have to find what is the level of the maturity of our code. Is this code is available for Exascale or not? So just a point for we have tried to find what is the industrial roadmaps, and just mention for only the one word for Total. This is our roadmap, and actually we have 3 petaflop machines in our research center, but it's not using for research, it's using for operational. And that actually 75% of this machine is using every day, every night. So next year this machine will be upgrade to 10 petaflop machine. That means generally we will have only 2 years after the first is the worst. That's our roadmap. And we know that until, let's say, 100 petaflop, our code should be correctly available. But we know that after 100 petaflop machine, we have to rewrite a lot of things. We have to invent, we have some breakthrough. And the question is, where are the limits of the exascale? Is it possible to have an exascale machine for an hero applications? That means one in the exascale machine? I'm not sure. If you are not able to find and to provide some breakthrough in terms of algorithm. But certainly we should use exascale machine for farming applications. We need exascale for UQ, we need exascale for a lot of industrial applications. So we know that we will use at least the exascale machine by farming applications. Let's say, for example, in total, we certainly will use 10 times 100 petaflop machines. But we don't know if we are using one exascale. So exactly the same thing for the aeronautics. And just I want to mention that the exascale is not the goal for us. To solve this problem, which is the seismic equations, we effectively have to solve an inverse problem. And this inverse problem needs at least a zeta-flop machine. That the exascale is only one step. And exactly the same thing for what we call the digital aircraft. The digital aircraft needs much more than exaflops applications. So, and just to mention that the increase of the capacity of the computing is not only a question of time. Effectively, for the oil company, we really don't care about the time because we are using only a cycle of 8 days for working applications. So the problem, the advantage of the HPC that as we change effectively the accurate modeling, that we mean that we have a better understanding of the underground. And actually the mesh is roughly 5 meters. And we need 50 centimeter mesh for discover new reservoir, new carbonate reservoir. That means for discovering new nano porosity reservoir, we need effectively to reduce the size of our mesh. So that means that's the reason why we need power, we need computer, but we need also new algorithm, we need also new modeling, physical modeling. So this is also a large application we need in Europe, and I know also in the US. That's for the petaflop for the smart cities, for developing the smart grids, for furnishing electricity everywhere. And that's a part of the important because it was a cost-cutting issue. For all applications, we will have to have a data management. That's the big important thing. That's one of the key issues. We need data management to reduce communication. So we have to in situ to reduce the size of your data and reduce the communication too. Of course, we need a poor management impact. We need to work with uncertainties, and that's the point. In fact, what is behind everything? We need to develop the best coupling between architecture, algorithm, and applications. That's the goal. Developing DSL, developing a lot of things as you wish, but we need to have a real optimization between architecture. That's the reason why we have to work with vendors. Perhaps not in co-design exactly, but we have to work with. Because our application is completely dependent on the architecture, and the algorithm too. So it's impossible to ignore the evolution of the architecture. And the evolution of the architecture, what is it exactly? It could be heterogeneous, of course, perhaps not by GPU, but only by also a large number of threads inside CPUs. That's exactly the same thing, which is a second level of parallelization between the CPU management and the accelerators. So, but we need to have to change our programming. We have to involve our level of parallelization of our applications. And one thing very important, we have to parallelize the time. Because a lot of PDEs we have to solve is time depending. For example, for the flows, Navier-Stokes application, all those equations we have to solve is time depending, so we have to parallelize the time. So we have to define new algorithm for increasing the splitting of the equations. And I think that Jackie mentioned that they came in and a lot of type of application, but of course, our new application is multi-physics, transportation, chemical, thermodynamicals, a lot of applications we are doing so. So we have to split, of course, these equations to be correctly in phase with the architecture. So the last point is the very fault-tolerant system and application. How is it possible to resolve your problem? And of course, yeah. So that's the way. So I will skip a lot of things just now. So there's the industrial application, including, of course, I'm obliged to mention that combustion here with the surfax, and I think Gabriel will present some application and on this point. So I will skip. I spoke about this one. So because we are in Europe and this initiative is founding, yes, thanks, is founding by Europe, we have to develop something which could be certainly more interesting in Europe than the rest of the world. And we have to define where are the strengths of the Europe. And I think we have a place in Europe which is dedicated to infrastructure, to developing infrastructure, and put at the tables a lot of millions of hours of calculation, exactly what is possible with the InSight program in US. I think we have a lot of application, effectively in astrophysics, cosmology, fusion, ab initio, working, okay. We have very good mathematician labs in Europe, especially in France. I'm sorry for you. So thanks. And we know that we are developing a lot of software with validation and application. But we have a lot of weakness in Europe, of course, because we have quite low ISV. We have the 30% of the market, but only 1% of the HPC revenues. We have quite no scientific library in Europe. We have quite no definition of standard of programming. We have a lack of data management. We have a lot of things depending on the rest of the world. So we need an international collaboration, of course. So that's the objective of the rest of the systems. So just I want to mention we list what are the key issues. Yeah, what are the key issues we have to solve. So and the objective of ESI 2 now is one by one to propose recommendation of R&D program to tackle one or more items of each there. So for example, there we have speaking of mesh generation tool, and Jackie mentioned AMR, which is adaptive mesh refining, but I'm not sure that's the way for Exascale. We have to reinvent something, and people in the world are working that the mesh should be a variable of the EDP by himself. And we're working on this point too, because it will be a real breakthrough on this point. Oh, okay, we are other people working on isogeometry for replacing mesh generation. So a lot of systems are doing, and we need that. So I will skip a lot. Yeah. Sure. Okay, that's my final in 1 minute. This is now where we are. We defined what are our vision of the Exascale programming just now. And one thing is very important, that I think it's important to do that. The Exascale programming is not bigger, only the petascale programming is different. And for tackle the program is we Exascale impose. And that this sentence is shared also by the DOE in US, and Exascale imposed to do something different and differently. That's the way. So the objective for working, the first at all, we have to define hierarchical algorithm with communication avoiding, the CAA, communication avoiding algorithm, based on graph, of course, based on a lot of things, but communication avoiding. Second point, that the multiphysics method with minimized data transfer, we shape the operating system and try to have a mesh generation tools with an in-situ data processing. So for that, we propose to have a big data and extreme computing workshop. The first one was in Charleston in US. Next one at the end of this month in Fukuoka in Japan. And the last one will be at the end of this year in Europe, specially dedicated to big data in extreme computing. And the last slide, this we have at the end of the last year, provided 8 fundamental, critical recommendations to Europe. The first one dedicated to ultra-scalable algorithm. Second one dedicated to resilience. The third one dedicated to big data. The fourth dedicated, very important, to couplers, because we are using multiphysics, and the couplers should be much more important than today in Exascale. Fifth, where's the fifth? High productivity programming model. That means MPI is not enough. We have to change something in MPI. We have to expose MPI to have a very, very, very important. MPI is only, I think, just to point the MPI. MPI is not communication avoiding between processors programming. So we have to change something there. 7.1 is the high performance computing. And the 8th, yes, this one is very dedicated to uncertainties and optimization. So thank you for your attention.